Okay, hello, Math Beyond Honors students. We've made it to the 1.1G lesson, abstracting the solving process. Uh, so this is a very good lesson to really hone down on your skills for isolating the variable. We're going to see many routes taken. I hope you've started to realize from all your practice that there are many ways to solve for the variable, right? We're so used to distributing or and all that, clearing the denominator, clearing the decimal at this point. But you should realize that you could use a variety of strategies to get to the answer. So let's just take a look at an example where we have 3 times the group, x plus 2 equals 12. And as stated in class already, you should already know that there are two ways, at least two obvious ways to do it. So let's take a look at Oliver's method. You can see how Oliver takes the 3, distributes the 3 to each term, and then creates a two-step equation and solves. Right? I think a lot of us would probably prefer Oliver's method. Sarah's method is something that we've talked about recently. I've talked about it in class. Just because you have a number outside of a group doesn't mean that you always have to distribute it. In fact, if you want to call it 3 times the group, right? 3 orders of something cost $12. Well, doesn't that mean that the group has to equal 4? Right? If 3 times 3 groups of something is 12, doesn't that mean 1 times the group is going to equal 4? Right? So it's kind of nice to think of it like that, and sometimes it can make your life a lot easier. And you could see how this is x plus 2 equals 4, and Sarah divided away the 3 where Oliver uh, distributed. They both are correct and utilize effective strategies, right? Effective strategies to solve for x, to isolate x. Okay, so you can kind of tell that what if we had pure variables, right? If you go into higher level math classes and you go into some science classes, you're going to have multiple variables. So if you get a situation where you see something like p times the group of x plus q is equal to r, you should still, if I told you to isolate x, you should still realize that your route, your whichever method you want to use to solve is applicable to variables as well. I know it's not as simple to think about because you're so used to calculating with numbers, but just think about this, right? If I wanted to use Oliver's method, which is to distribute, I would do p times x plus p times q is equal to r, right? P times x plus p times q is equal to r. And then what I would do is I would subtract the entire PQ to the other side, right? Because this is kind of like a constant. Remember how it was like in the previous, it was 3 times 2. Well, in this case, it's just PQ. This is a kind of like a constant or just a term, right? Our goal is to isolate x here. So I would then subtract PQ from both sides, and I would get PX is equal to R minus PQ. And then our final step would be to divide both sides by P. And this gets a little bit complicated, but you get X is equal to, I'm just going to call it R minus PQ divided by P. Now, there are multiple ways to write this. You can see how there's a P, there's a term with a P value, and there's a P on the bottom. So you could actually simplify that a little bit, but just because it's like this doesn't mean it's wrong either. And I actually would accept it like that. But I will admit that Oliver's method is actually not really that clean. It kind of gets a little bit messy the way it was written. And let's just see if Sarah's method, when we divide away the value of p, maybe that's a little bit cleaner, right? So instead of distributing, I'm going to divide both sides by p, and I end up with x plus q is equal to r divided by p. And I then will just subtract q from both sides, and now I get x is equal to r over p minus q. Now the question is, are these two really the same? Take a moment to look and tell me if you believe that these two are the same. Are they equivalent? Technically, if I did r minus pq divided by p, right, r minus pq divided by p is equivalent to r over p minus a full q, right? Because you could see how the p values cancel over here, and there's obviously you still have to do r divided by p, and you get rp, and then minus, when you divide this, you just get a singular q, right? So this lesson will be solving for a variable given an expression or equation with all variables. It really, really kind of pushes you to, uh, it pushes your understanding of how to isolate a variable, right? We're so used to isolating x given numbers next to it. What happens if you're given a situation like a times b plus 2n equals y, and they tell you to solve for n, right? Okay. So if there's one recommendation for me, I would say try to avoid distributing, right? Try to avoid distributing actually, because distributing can make your steps a little bit messier and more complicated than if you just were to divide, right? So my tip would be to try to avoid distributing and basically try to utilize Sarah's method. Okay, so in number 3, you can see how we're trying to isolate the variable n. So what I would do first is I would divide both sides by a, right? I'll write this down again. A times b plus 2n is equal to y. I wouldn't distribute the a because that would make things more complicated. I would just divide both sides by a, and I get, now this is going to get kind of messy already, but I get b plus 2n is equal to y over a. Okay, so then now our goal is to isolate the variable n. So you just subtract b from both sides, right? And then you get 2n is equal to y over a minus b. I know that's a little bit weird. It looks weird to do that. And then what I would do after this is I would multiply the entire thing by 1/2. Now every term gets hit by the 1/2. And I end up with n is equal to, you could write it like 1/2 y over a minus b. And that would technically be okay. But there are other ways you could write this too. You could write it as n is equal to y over 2a minus b over 2. And yeah, your answers are going to look pretty complicated like that. So it is pretty intense. Um, but you kind of have to realize we are at that stage in our mathematical careers now. We are at the stage where even isolating a variable, given only variables, is something that you need to be comfortable with. Okay. All right. Let's keep going. So this lesson is kind of, it seems short, but it's definitely fully loaded. You want to make sure, I would recommend that you do the entire thing. Let's take a look at number 4. It says, explain the mistake made when solving for W in the equation, and solve for W correctly. Okay, so let's just take a look. W plus T divided by 3 is equal to N. Okay, so I can see what this person did, multiplied both sides by 3. And so if you multiply the entire thing by 3, right, you do get the left side canceling with the denominator of the 3, and the 3 cancel. So that's what you want to see. But this person, what did this person forget to do? Does anyone already see it? This person forgot to multiply the right side by 3. Right? If you want to multiply the entire thing by 3, the entire equation, you cannot forget about the right side, right? So I'm going to go ahead and just continue on from this step. W plus T is supposed to equal 3n, not just n, 3n. And then you want to solve for W, and that's simple. Then you just subtract T from both sides, and you get W is equal to 3n minus T. Okay. Whew. So 5 through 12, awesome problems to practice with. I recommend you do all of them. And if at this point, I would say go ahead and pause the video. We're only 12 minutes in, but please try these problems on your own, and then look at the problems, or look at the, write down all the answers, see how comfortable you are, and then check the answers with the notes and see if you got them right. There are so many strategies you can use at this point. You could even cross multiply. So like for something like number 9, let's talk about it. I could actually just cross multiply 5 times 6a, and that has to equal 28x. It says solve the following equations for x. Okay. So there is cross multiplication potential here. So I'm going to write cross multiply, and basically if I just take the 5 times the 6a, I can set it equal to the 4x times the 7. So let's do that. 5 times 6a is going to be 30a, and then this is going to equal 28x. Now, for those of us that are wondering why we're allowed to cross multiply, you could think of it as, I'm going to rewrite this problem, 5 over 4x is equal to 7 over 6a. You could think of it as, I'm multiplying the entire thing, class. I'm multiplying both terms by really the product of the denominators, right? The product of the denominators would be 24ax. And if I multiply the right side by 24ax and the left side by 24ax as well, what you would get is you end up getting 5 times 6a and 4x times 7. And that's really what cross multiplying is. Cross multiplying is basically just multiplying the entire equation by the product of your denominators. I can explain that in class if you still need that to be more clear. Okay, we're solving for x, so now all I have to do is divide both sides by 28, and obviously you still want to simplify 30 over 28. Okay, so x is going to equal 15a over 14. Anything can be cross multiplied. So something like number 10, you could also make 5 over 1, and then cross multiply this, right? So you get ax plus b times 1 is equal to 5c. So ax plus b times 1, which is itself, is equal to 5c. So now we're trying to isolate x, subtract b from both sides. Just like a constant, you always get rid of